morning, students. Today we are going to learn a new topic which is having a great prominence in our physics, that is the special theory of relativity. So coming to the special theory of relativity, we need to know what is relativity first. So let us discuss some basic things based on which we are going to determine the position, the length, and the time, and many other physical quantities, fundamental physical quantities with which we are able to represent a particular system, or else when a body is at a particular position, it has to be determined by specific coordinates. So let us look into the basic fundamental quantities now. So what is relativity? As you are looking into the slide, the first slide has the length is relative. See the slide. So in this, what is that? The length is relative. See, we are observing there 4 sharks which are of different color. So when we come to that grey shark, it is the largest and it is of more length than that of the other 3 sharks. So now when you come to that red shark, which is in between the the purple and the grey, so which is lesser length, which is having lesser length than to that of the grey shark, and which is having more length than that of the red one. So looking at that picture itself, you will be able to understand that. So length is relative. So with respect to grey shark, the red one is smaller in length, but when compared to that purple one, the red one is of greater length. So length is relative. Next, coming to the position. The position where we are standing, or the position where we are going to observe anything, is always relative. Yes, is always relative. So let us find it out through this slide. I have just taken one of the pictures. In recent Commonwealth Games, Saina Nehwal has won the gold medal in that single badminton championship. So the gold medalist is standing in between the silver and that bronze medalist. So when you observe, for the silver medalist, Saina Nehwal is on to the left hand side. When we come to the bronze medalist is standing exactly to the left of Saina Nehwal. So the gold medalist is relevant to both of them with some relative positions. So both are correct in respect to their positions where they are standing, but how we are observing as an observer is different. So position is also relative. So now we shall come to the size. Size is also a biggest property where we can say that the size is also relative. So looking into the slide, there I have just placed Earth and our planet Earth, and Venus, Mars, Mercury and Pluto. So when we compare the sizes of these planets, so Venus comes next to the Earth. So Venus is of lesser size than of the Earth, but is of more size than that of Mars. But when it compared to the other planets, so Venus is of more size than that of the other 3 planets except Earth. There in this figure I am just pointing out. So size is also relative. So next come to time. Time is always relative. As we ask anyone, as we impose a question on anyone that what is the time now? So a person living in India will point out with some other time, and where it comes to an American, he will be telling about some other time because he is there in the other part of the world. So it depends upon the position where the person is. So time is also a relative quantity. Then comes motion. So motion is also a relative. See, we are observing a train there. So in a train, there is a body which is holding the ball, which is in white color. There you are able to view that in first compartment, and the other observer is on the outside, which is in blue color. So the passenger who is traveling inside the train holding the ball, for him the ball seems to be in stationary position. But when it comes to the observer who is outside the train and observing the train which is in motion with some velocity moving, so for him the ball is traveling with the same velocity as that of the train. So the motion is also relative. So from all these conclusions we can say that length is relative, position is relative, size is relative, time is relative, and motion is also relative. So all these things are relative. So what is the link between them with respect to our title of the present topic, special theory of relativity. So the theory which deals with the relativity of motion and rest is named as the theory of relativity. So every object which is in motion or else the object is in rest, so based on the velocity of the body we can impose that to the theory of relativity. So coming to the theory of relativity, the theory of relativity has been divided into two categories, two theories. So they are special theory of relativity and the other one is general theory of relativity. So let us know today what is special theory of relativity. So when it comes to special theory, in this theory we deal with the objects or systems which are moving with constant speed or constant velocity, or else the objects which are at rest with respect to each other. Similarly, when it comes to general theory of relativity, here the objects are or else the system is moving with some speed which is rising, which is increasing in the increasing section, or else it is getting accelerated, or else it is getting deaccelerated, where I have pointed out in the slide as it is speeding up or else slowing down with respect to each other, with respect to each of the objects which are present in that system. If they are speeding up or else slowing down with respect to each other, it comes under general theory of relativity. Now let us go to our topic of concern today, that is special theory of relativity. So who has proposed this theory? First of all, let us know. So first, Sir Albert Einstein in the year 1905 has given the special theory of relativity. And what is this relativity? It is the generalization of Newtonian mechanics. See, Newtonian mechanics is always called as a classical mechanics, where it is failed to deal with the objects or else the particles which are having velocities very much approachable to the velocity of light. So it is failed to deal with the objects which have more velocities approaching near to the velocity of light. So this failure can be treated as a failure. So this failure can be rectified by some other theory which was proposed by Einstein, special theory of relativity, where in this theory the velocities of the objects which are very much approachable to the velocity of light can be like observed, and the motion of the object can be given, and everything can be described in that system which is approachable, whose velocity is very much approachable to the velocity of light. As I have written there, the velocity of light, all of you know, it is denoted by c, and it is a universal. Velocity of light is always universal, constant, and that is 3 into 10 power 8 meter per second square. So what is the importance of this special theory of relativity? It is very much important to the micro world, that is the subatomic particles which exist in this world. What are the subatomic particles we have? Electrons, protons, neutrons, and quarks, mesons, bosons, whatever the particle it may be. So all the subatomic particles' motion and the velocities with which they are moving. And when it comes to the nuclear reactions, interactions, so everywhere this relativistic mechanics plays an important role. So in order to study the motion of any object, in any place, we need to have a reference point. So let us consider a running race, which we always do, which we always play in our childhood. See, running race, how do we do that? So we put a reference point from which we will start up our race. So that from that position we will be based on the distance in a particular time, how much you have travelled, that gives you the velocity with which you have travelled, and based on that who is the first in the running race can be known. Similarly, we need to have a reference frame from which we can know the motion of a body. So the motion of a body has no meaning unless it is described with respect to some well defined coordinate system. So the coordinate system which describes the motion of a body is named as frame of reference. So any system relative to which the motion of an object can be described is called as frame of reference. As we have discussed now, a perfect example is the running race. Now coming to the frames of reference, there are two types of frames of reference. So they are inertial frame of reference and non-inertial frame of reference. So let us come to the inertial frame of reference. So a body in which, if at all it is not acted upon by an external force, if it is rest or moves with a constant velocity, then such type of frame of reference is named as inertial frame of reference. That means here all Newton's laws are valid. That is, law of inertia of Newton proposed as the first law of Newton, in which every body continues to be in rest or it moves with a constant velocity until and unless an external force is applied on it. So when all the Newton's laws are valid in such a frame of reference, the frame of reference is said to be an inertial frame of reference. So now coming to the next frame of reference, which we already told, they are non-inertial frame of references. So when the name itself depicts that this is not an inertial frame of reference, that is, the Newton's law of inertia is invalid in this frame of reference. So a body not acted upon by an external force, when it is accelerated or moves with an increasing velocity or else a decreasing velocity, such type of frame of reference is named as a non-inertial frame of reference. So here the Newton's laws are not valid. So now what is the Newtonian principle of relativity? If Newton's laws are valid in one reference frame, then they are also valid in another reference frame, moving at a same uniform velocity relative to the first system. If I take one system, then the other system is also moving with the velocity relative to the other one, previous one, with uniform velocity, then such type of mechanics can be dealt in this Newtonian principle of relativity. This is referred to as the Newtonian principle of relativity, or it can also be known as Galilean invariance. So according to Galileo, he has given some transformation equations which we will be going through in the next slides. So according to him, if Newtonian laws, all the Newton's laws are valid in that frame of reference, then he has proposed that called as Galilean invariance. So when we consider inertial frames K and K dash as we are observing in this figure, so see, we have represented there two frames of reference, they are K and K dash. So where K is in three-dimensional, that is x, y and z coordinate axis, and similarly K dash is also having x dash, y dash and z dash coordinate axis. So where O is the origin for K and O dash is the origin for K dash. So now K dash is the frame where, well, K is the frame which is at rest and K dash is the frame which is moving with a constant velocity V bar as shown in the figure with respect to the K. With respect to K, here you are observing that V bar. So I have written there K is rest and K dash is moving with the velocity V bar, where V bar is the velocity of the frame K. So both the axes are parallel to each other as we are seeing in that diagram. Then what are the Galilean transformations? So for the Galilean transformations, we use this frame of references K and K bar, K dash. So now coming to that, to transform the coordinates of position and time from one inertial frame to the another frame, we use Galilean transformations. So what is the usage of Galilean transformations means? When we want to observe a point from a particular frame of reference K to a particular frame of reference K bar or K dash, which is moving at the uniform velocity with respect to K. So we use these transformation equations in order to represent the position and time coordinates of a particular object. So as you are observing here in this thing, in system K, the position of a point P as we are showing here can be represented by the coordinates x, y and z here, and we have the time coordinate t. So then when we come to the system K dash, we have the point P which is observed at coordinates x dash, y dash, z dash and t dash. So with this what we can say is the position of a point with respect to the frame k bar and k dash can be observed here. So when we come to this position with which the frame k dash is moving with the velocity v bar, so the position vector x dash or x can be represented as x minus vt, where x minus vt is the velocity of the frame k dash which is relevant to the frame k. So x coordinate I have represented as x minus vt, where k dash is in moment with k bar in parallel direction with constant velocity v dash. So x dash coordinate is x minus vt. Now the equations below which we have shown are called Galilean transformations. So where x dash from frame k dash is x minus vt, where x and t are the coordinates of the point P when we view from the frame k. Similarly, y dash is equal to y when we are observing the point y dash, we are observing the point P from frame k dash. Similarly, that is equivalent to y, which is the point coordinate, y coordinate of point P when the position which we are of point P which we are observing from the frame k. Similarly, z dash is the z coordinate of the point P when we are observing from frame k dash, which is equivalent to z. Since the frame is parallel to, moving parallel to, as we have seen in the previous slide, the frame is moving parallel to the previous frame in x direction, in horizontal direction with respect to velocity v. There is a change in the position with respect to x coordinate, while the position of y coordinate and z coordinate will be same, will remain the same. Now coming to the equations here, the time t for all the observers is fundamentally invariant, that is the same for all the initial observers from which frame we are observing. So hence t dash is also is equal to t. So only the position coordinate with respect to x axis has changed as the frame is moving in the x direction, right. So x dash is equal to x minus vt, while y dash is equal to y, z dash is equal to z, and t dash is equal to t. These equations are nothing but termed as Galilean transformations of position. Next comes the inverse relations of Galilean, where we are replacing the velocity vector v bar with minus v bar, means the frame is moving in the opposite direction with respect to the frame initially set at k. The k dash is moving in the opposite direction with velocity v bar. So opposite direction with velocity v bar itself we can designate it as minus v, where we are showing in the slide. So then what we have to do is the primed and prime quantities like x dash should be replaced by x, y dash should be replaced by y, and z dash should be replaced by z, and t to be replaced by t dash. So doing these two steps we will be arrived at our inverse relations as they are shown in our equation now. So x is equal to x dash plus v bar t. If you observe in the previous equation I have given as minus vt, but here since the frame is approaching in the opposite direction we are representing as x dash plus vt. Similarly, y is equal to y dash and z is equal to z dash and t is equal to t dash. So these are the inverse relations of Galilean transformations. Now we will come to the main thing of today's topic, that is the ethers hypothesis. See, we have accepted the wave theory of light long back, and because of that wave theory of light we have which has led to a thought that a space is filled with a substance called ether. So the space is termed to be filled with a substance called ether and which is surrounding our earth in continuous fashion. So that ether terminology has been proposed so that we can represent any physical quantity like velocity. For suppose if the velocity of earth can be calculated using this either as a stationary frame of reference, that is inertial frame of reference. So then this frame of reference can be used to find out any physical quantity which is relevant to the frame of reference, relative to the frame of reference, called either frame of reference. So how do the scientists have predicted? So either was supposed to be invisible, massless, perfectly transparent, and which is always a non-resistive, and having low density and high elastic medium, which is proposed as an either medium. So we have to know now whether the relative motion between the earth and the other medium, which is termed as either, can be detected. So whether the relative motion between the earth and either can be detected, let us go into the depth of this concept. So in such a motion, if such a motion can be detected, then we can choose a fixed frame of reference in the stationary either, and we can express all motion relative to this frame, as I have told you before. So we can so determine the absolute velocity of the earth using the frame of reference. Which is the frame of reference now we are going to have? The either frame of reference, where either we have considered to be a perfectly elastic one with high elasticity and low density, and which is a massless and non-resistive. So now we are going to the either medium. So who has done the experiment? In order to, he has done an experiment. The Michelson and Morley has conducted an experiment in order to determine the absolute velocity of earth with respect to the frame of reference named as either. So either is an assumption, absolutely it's an assumption made by Michelson and Morley to conduct this experiment. So when did they do this experiment? In 1887, Michelson and Morley set out to measure the relative velocity of the earth with respect to the either. So Albert Michelson, he is of period 1852 to 1931, was the first US citizen. So remember, he is the first US citizen to receive a Nobel Prize for physics. So the Nobel Prize which he has received is in 1907, and he is the first US citizen to receive a Nobel Prize. So what is the experiment? What did he do? He has built an extremely precise device which is termed as an interferometer. See, the name itself is showing as interferometer. Interferometer, it's based on the interference between any two waves which are in motion. So the Michelson interferometer is used to measure the minute phase difference between any two light waves traveling in mutually perpendicular directions, either mutually perpendicular or mutually orthogonal. If any two light waves are traveling in two mutually perpendicular directions, so then the phase difference between the two waves can be calculated. Based on that, the path difference can be calculated by using this interferometer, where the two waves will be getting interfered after some time. So the interference itself is there in this interferometer. So it is termed as interferometer. So then this is the figure where we have interferometer, where we have a monochromatic light source from which the monochromatic wavelength of light is getting emitted. So we will make the light to be parallel, collimated by using a lens here. So then the light gets parallel and it is passed through some slit S, so that the beam will be narrow, and this light ray is made to fall on a semi-silvered glass plate here. This is a partially silvered glass plate, as you can call it as a mirror, as it is coated by silver. So this partially silvered glass plate is A here. So the light wave incidented on that is coming from the source of monochromatic wavelength. So it has single wavelength, let it be lambda. So now the wavelength, the light ray which is falling on this semi-silver glass plate, as it is semi-silvered, a partial light ray will get reflected, as it is shown here. It is getting reflected towards a mirror M2. towards D, where the point is D, where the first light ray is getting reflected. The other light ray is getting transmitted through this partially silvered glass plate. So, and that transmitted light ray is again moving in this direction, and it is falling on a mirror M1 here, which is placed at a distance. So, if you suppose that optical length between this silvered glass plate, partially silvered glass plate or semi silvered glass plate A, to that of mirror M1 is L1, to that of M2 is mirror M2 is L2, then L1 is made equal to L2 by using a compensatory glass plate, which is shown here, which is called a B. So, these two lengths from this partially silvered glass plate to that of mirror, and this the ray which is falling transmitted through this partially silvered glass plate to that of mirror M1 are at equidistant. We will make them equidistant, like L1 is equal to L2 later in the theory, where we derive the path difference between the two rays. See, as you observe here, see here, AC, the light ray AC is moving in the direction of the velocity of the earth, that is velocity of the ether which is surrounding the earth, that is V bar, but it is in the longitudinal direction. But when this ray, when we come into this ray, this is perpendicular to the longitudinal direction, that is, this is the transverse component of the reflected ray. This is the longitudinal component of reflected ray along the length of the wave which it is passing. So, this is the telescope where the first ray which is getting reflected from mirror M2 and the second ray which is getting reflected from M1 will come and pass through this. Well, they will meet again at the point A, and again they will get interfered here, and the interference pattern can be observed through this telescope which is at point E. So, now coming to the theory where we are deriving the phase difference or the path difference, the time difference with which the two rays are travelling. Now, in the second slide we will be showing that. So, here we have AC is parallel to the motion of the earth during an ether wind. A light from source S is split by mirror A and travels to mirrors C and D. Here the mirror A means that is a semi silvered glass plate A, and travels to mirrors C and D in mutually perpendicular directions. So, after reflection the beams recombine at A slightly out of phase due to the ether wind as viewed by the telescope E. The typical interferometer fringe pattern observed when the system is rotated by 90 degrees is given by this figure which we have shown here. That is the fringe pattern observed through the telescope E when the entire system is rotated to 90 degrees. That is, the mirror M1 becomes M2 and M2 becomes M1. So, now this is the relevant schematic diagram of Michelson-Morley experiment, which is more appropriate for you to see now. See, this is the rest frame where the mirror M1 is at rest, and this is the M2 mirror M2. So, now the length between the semi silver glass plate and the mirrors is kept constant as L, which is approximated here as 1 meter. So, here when we suppose that when the frames are at rest. So, the frames are rest means the mirror M1 and M2 is at rest, there is no motion, that is at the rest frame. So, the time travelled from by the transmitted ray from the semi silver glass plate to the mirror M2 is equivalent to the time travelled by the reflected ray from semi silver glass plate to the mirror M1. So, there is no time difference. So, there is no path difference. So, there is no any phase difference between the two rays. But as earth is moving with some velocity, uniform velocity V bar, So we have the moving frame here, which is shown in the diagram here. So here in the moving frame, see, this is the initial position of the semi-silver glass plate A. So after, when it is traveling with some velocity v, so it is traveled to this position after some time t here. So now the ray is not exactly going here perpendicular in the perpendicular direction, but it is traveling in this way, and it is getting reflected back by the mirror, and again it is traveling through this path, and it is reaching the semi-silvered glass plate G again here. So obviously, as the moving frame is moving, this mirror is moving, the semi-silver glass plate is also moving with respect to the velocity of the earth. So we have the moment of frame, moment of mirror m1 or m2, means there is a moment in the semi-silver glass plate also. So this can be calculated, the time travelled by the ray, the reflected ray from the semi-silver glass plate, the total time travelled by the semi-silver glass plate, and the total time travelled by the transmitted ray from this glass plate. See, the ray is going here and it is coming back reflecting from the mirror m2. So the reflected ray and the transmitted ray both travel in two different directions which are perpendicular to each other, and they all the way come here and combine here and form an interference pattern which is observed through our telescope E. So now I will show the equations which are analyzed based on the theory which we have seen now. So assuming the Galilean transformations we are assuming here, then the time t1 from A to C and back, that means A to C here. In this slide we are seeing the time travelled from A to C and back is given by the equations here. Similarly, the time t2 from A to D and back is given by the equations here, where we know that the distance, the velocity of any object is the displacement in unit time. So c plus v is the relative velocity of the frame moving with the velocity v bar. Similarly, c minus v is the velocity of the earth, relative velocity of the earth. Then, so that the change in the time is given by t2 minus t1, which are given by these equations. So now upon rotating the apparatus in the optical paths lengthen L1 and L2 with respect to 90 degrees, so we will get delta t dash is equal to t2 dash minus t1 dash as they are given here. So thus the time difference between the rotation is given by this one. So delta t is approximately equal to v square into L1 plus L2 by 1 minus v square by c square. So when we approximate it to binomial expansion, assuming v by c is much less than 1, this reduces to this equation, the above equation reduces to this equation. So from this equation, from the above mentioned equation, this equation, where we equal L1 and L2 to be L, which is of 1.2 meter, and the velocity of the earth's orbital speed, that is velocity of earth, to be 3 into 10 power 4 meter per second, the velocity of the frame, so that the time difference becomes delta t minus delta t is equal to v square into L1 plus L2 by c cube. So we substitute L1 as 1.2 and L2 as 1.2 and v as 3 into 10 power 4. So we get 8 into 10 power minus 17 seconds. So the expected fringe shift based on this experiment should be of 0.4 fringe. But here, after doing this experiment, the fringe shift was observed to be 0.01 fringe. So which is very much less when compared to that of 0.4. So Michelson and Morley have conducted this experiment repeatedly at different points on the earth's surface and in different seasons of the year at different positions of earth, but they could not detect any measurable fringe shift which they have approximated as 0.4 fringe. So Michelson have concluded big conclusions, really very advantageous conclusions based on the above experiment which they have done. They are Michelson as he has assumed that there will be a measurable shift, but he could not able to measure the measurable shift. So this result can be termed as a null result or a negative result. Hence it is impossible to measure the velocity of the earth relative to the ether, and which leads to the total rejection of this hypothesis. So the entire ether hypothesis is negative. That means the ether does not seem to be existing. So ether is not existing here, and where we have, I mean, the Michelson-Morley has thought that there is a medium called ether, and which is moving with a velocity v, constant velocity v bar, and from that medium, from that frame of reference of ether, we can determine the velocity of earth, but entirely the conclusion has got negative result. So the possible explanations for this negative result was given by in different manner. So the first and famous explanation for the possible negative result is the ether drag hypothesis. So this hypothesis suggested that the earth somehow dragged the ether along as it rotates on its axis and revolves around the sun. Since earth is revolving around the sun and earth is also a moving object, so earth seems to have dragged that ether medium with itself. So hence, as the earth is dragging the ether with itself, so it seems to be that the ether, there is no considerable fringe shift between those two. But this hypothesis, the ether drag hypothesis, is also a contradictory, and it got contradicted by a theory called stellar aberrations, in which the aberrations of light from the stars can be measured. So when they have measured some conducted some experiments on these aberrations, they have concluded that this ether drag hypothesis is not exact explanation for the negative result of Michelson and Morley's interferometer experiment. So then the other theory which has come in front of us is the Lorentz-Fitzgerald contraction. Based on this contraction, the Lorentz and Fitzgerald, these two scientists, have given that the length need to be contracted by a factor of √1 minus v square by c square, which is making in the path lengths. So because of this, there may be a zero phase shift, which resulted in a non-considerable phase shift or its fringe shift. So this, however, this is also an ad hoc assumption, and this could not be experimentally verified. So this is not all, this also couldn't explain clearly the negative result of this Michelson and Morley experiment, that the ether medium can be stationary and it can give the velocity of earth to its absolute value. Then Einstein has come up with some postulates. So all these theories have failed to determine the exact velocity of earth with respect to the frame ether. So ether doesn't exist. So it has been concluded by all these theories, and Einstein, Albert Einstein, has come into picture, and he was only 2-year-old when Michelson and Morley has done the experiment on this ether, and where they have executed the result as null. Then at the age of 16, when Einstein began thinking about this experiment and the result of ether hypothesis, then he has come up in 1905, when he is of age 26, that there is a principle called a principle of relativity, which he is believed as to be the fundamental principle, where in this principles he has given two principles of relativity. They come as postulates. So among them, the first one is the principle of relativity. So in principle of relativity, all laws of physics are same in all inertial systems. So everywhere, whatever inertial system you take, all the laws of physics are valid when the inertial system is at uniform velocity. So then the second postulate is of very much importance, that is the constancy of the speed of light, that is the speed of light is constant. That means the observers in any inertial frame can measure the same value of the velocity of light in a vacuum. This postulate expresses the result of Michelson and Morley experiment. That means the velocity of light in vacuum is same if you observe from any type of inertial frame of reference, where inertial frame of reference means all the Newton's laws are valid. So only the theory which explains the negative result of Michelson-Morley experiment was given by Einstein is the second postulate, where the constancy is there in the speed of light. So all today we have seen what is the relativity and how time is relative, how position is relative, how the motion is also relative, and based on that the motion is relative, or the motion of an object is relative, or else it is the motion of an object is not there, that is the object is at rest. So all these, the motion of any object which is in motion can be known through the equations of Newtonian mechanics. So this Newtonian mechanics is not able to explain the theories in which the velocity of the objects is approachable to the velocity of light. So a special theory of light, special theory of physics has been come into the picture, called special theory of relativity. So based on this experiment, we can say that there is no other frame which can give the, other than on the surface of earth, which can give the velocity of any other object which is in the inertial frame of reference. So by this thing we will conclude today. Thank you.